Hello everyone, this is our third lesson, chapter 6, kinetics. We'll speak today about rate equation or rate expression. This is the first lesson in the higher level topics. Let's get started. For today's lesson, I will explain the terms rate constant and order of reaction, work out the rate expression, which is the rate equation from numerical data. Before we go ahead start speaking about the rate equation, we have to agree about some main points regarding the rate of the chemical reaction. There are several ways of measuring a reaction rate. If we'll study the reaction of calcium carbonate, CaCO3, with the hydrochloric acid, we already know that the product will be CaCl2 and carbon dioxide plus water. Our main concern will be with the carbon dioxide because it is the gas that will be given off from this equation or from this experiment. So if we have a gas which will be given off, we could simply measure the amount or the volume of the gas being given off per second at any particular time, and this will give us an indication about the rate of this chemical reaction. It is obvious that if we have 2 and 1 rate 2 and rate 1, how I may know that this is rate? Because it is volume per time. Volume per time. So the rate here for 2 is twice as fast as 1. The rate of a reaction is measured in terms of how fast the concentration of one of the reactants is falling. Okay, so we are speaking about how the reactants are used up, how the reactants amounts is used up per unit time. Its unit here is representing the concentration of the reactants per time. Now let's go ahead start speaking about the rate equation for the reaction that we have here. A plus B is giving C and D. Let's suppose that you have done different experiments to check how the change of the concentration of A will affect the rate of the reaction. Okay, so we have done some experiments to check how changing the concentration of A will affect the rate. We have only three possible scenarios. Only 3 scenarios. These are the scenarios that we will study. Scenario number 1. You increase the concentration of A, nothing happened to the rate. Doubled the concentration of A, nothing happened to the rate. Multiplied, increased the concentration of A by a factor of 4, nothing happened to the rate. So here we can say that A, the concentration of A or reactant A is not affecting the rate, because simply when we started changing this concentration, nothing happened to the rate. So the rate of reaction is not proportional to the concentration of A. This is our first scenario. Our second scenario, the rate reaction is proportional to the concentration of A. Again, why I'm saying concentration? Because square brackets, when we are drawing square brackets, we mean concentration. We mean the concentration or refer to the concentration. In our second scenario, we have found that when we double the concentration of A, the rate doubles as well. When we increased the concentration of A by a factor of 4, the rate goes up 4 times as well. Okay, so we have to understand that the rate is proportional to the concentration of A. And we can write an expression which is rate is related to the concentration of A, square brackets mean concentration in mole per dm cube. And this is the proportionality sign. We will borrow something from mathematics here. If we would like to remove this sign, this proportionality sign, we have to use a constant. Our constant that we will introduce now is the rate constant, which is K. So in our second scenario here, rate is equal to K multiplied by the concentration of A. And we have to always remember that in this scenario, scenario number 2, when we double the concentration of A, rate doubles. Okay? The scenario number 3, or the third scenario. In the third scenario, we have something else. When we doubled the concentration of A, the rate would go up 4 times. What is that? The rate reaction is proportional to the square of the concentration of A. Again, the rate of the reaction is proportional to the square of the concentration of reactant A. When you double the concentration of A, the rate will go up 4 times. When you triple the concentration of A, the rate would increase 9 times. What does it mean by 9 times? It is 3 to the power 2. So we can say that the what will happen to the rate is square the effect that will happen to the concentration. Square the effect that will happen to the concentration. And if we would like to use our sample term, we can say that the rate is proportional to square the concentration of A. And of course, as we agreed from a while, to remove this sign, we have to introduce a constant, which is the rate constant, So again, we have 3 scenarios. Scenario number 1, rate is not proportional to A. When we increase the A by 2, increase the A by 3, increase the A by a factor of 4, nothing happened to the rate. Scenario number 2, we double the concentration of A, the rate doubles. Multiply the concentration by a factor of 4, the rate has increased by a factor of 4. So the rate is proportional to the concentration of this reactant A. Third scenario, the rate of reaction is proportional to the square of the concentration of A. So if you double the concentration of A, the rate would go up 4 times. If you triple the concentration of A, the rate would increase 9 times. We have here, this is our rate equation. Rate, which is, it has a unit of mole per dm cube per second, concentration per time. We have here K, rate constant, that we have used to remove the proportionality sign. We have here the concentration of the reactants. Let's use another color. We have here the concentration of A, concentration of B. What is this power? The power now that we will speak about it in the next slide is the order of the reaction with respect to A, and this is the order of the reaction with respect to B, which is reflecting this order. This order is reflecting what has happened to the rate of the reaction when we have changed the concentration of the reactant A or B. And we have here the concentration of the reactants. So this is called the rate equation. The concentrations of A and B have to be raised to some power to show how they affect the rate of reaction. So this power, the order of the reaction, this power which is representing the order of the reaction, is reflecting how the change in concentration of the reactants will affect the rate. These powers are called orders of reaction with respect to A and B. So to summarize what we have discussed about the rate equation, the rate equation is giving us an indication about how the concentration is related to the rate. It links the rate of the reaction to the concentration of the reactants. When we are writing R is equal to K concentration of A, so we should understand that if we doubled A, R will be doubled. If we put here power 2, so it means that doubling A will increase R by a factor of 4. Okay, so this is the first important point about the rate equation. It cannot be detected, or this rate equation cannot be written, cannot be figured out without an actual experiment. We should have an actual experiment. It cannot be just found from a normal chemical equation. We should have an experiment. We should have data given from an experiment that tells us that, okay, when you double the concentration of A, the rate will double. When you multiply the concentration by a factor of 2, the rate has increased by a factor of 4. Okay, so we should have data coming from actual experiments. So we have here a chemical equation. Chemical equation will never give us any indication, or it will never be used to predict the rate equation. Here is a rate equation. This rate equation, if this is a possible rate equation, so it's telling us that if you double the A, the rate will double, because as you can see here, there is no power to the power 1. But with respect to B, if you doubled B, R will be quadruple. The rate of the reaction would be quadruples if you doubled the concentration of B. R, which is the rate of reaction, it is, of course, its units is reflecting the concentration per time. We have K, which is the rate constant. Its units is depending on the rate equation, and we'll study in the next slide how can we predict its units. Catalyst, of course, the catalyst is speeding up the reaction, so it is very important to include it in the rate equations. We have just mentioned something about the order of the chemical reaction. When we are writing R is equal to Ka, so the order of this reaction is 1 because there is no power. If we wrote R Ka to the power 2, this is the order. To the power A is raised to the concentration of A is raised to the power 2, so the order is 2. We have what's called individual order. What's the individual order? It's the power to which a concentration is raised in a rate equation. Can you see here? This is the order of the reaction. Here we have it is 1, but we don't write 1. The overall order, if we have here a rate equation A and representing A and B, we can see here. Okay, let's see the example that is given here. We have here the concentration of A and the concentration of B. It's clear from the rate equation, that the order with respect to A is 1 because it's raised to the power 1. We call it first order. The order with respect to B is 2. Why? Because we have here power 2. The overall order is the summation of the individual orders in the rate equation, so it is third order. Everything is third order. But with respect to A is 1 because the concentration of A is raised to the power 1. With respect to B, it is 2 because the concentration of B is raised to the power 2. Now, what is the units? What are the units for the rate constant K? We can derive the units from the equation. How can we do that? Let's check. It is pretty easy. The rate equation for zero order reaction. What is meant by zero order reaction? Zero order reaction is scenario number 1 that we have mentioned earlier. What is zero order reaction? The rate is not the rate of the reaction is not proportional to the concentration of the reactant, one of the reactants. This is called zero order. This is called zero order. What does it mean by zero order? Again, concentration of A is raised to 0. So changing the concentration of A will never affect the rate, will never affect the rate. Doubling the concentration of A is not affecting the rate. This is called zero order. So R is equal to K. R is equal to K. What is the unit of K? Of course, it will have the units of R rate, which is the units for the concentration per time. What if we have first order? What is first order? If we have R, which is equal to K multiplied by the concentration of A. K here, the units of K is second to the power negative 1. Why is that? It's very, very easy. Why? Because K, in this case, K is equal to R over the concentration of A. What is the unit of R? It is mole by dm to the power negative 3 by s second to the power negative 1 all over concentration of A. What's the concentration unit? It's mole by dm to the power negative 3. So it will be cancelled out with this. So the leftover is second to the power negative 1. This is how we can derive the unit for the rate constant for the first order reaction. What about the second order reaction? Second order reaction, we have R is related to, R is equal to K multiplied by square the concentration of A. K here has these units. How can we derive it? Same idea. K is equal to R over the concentration of A to the power 2. We have mole by dm to the power negative 3, mole to the power over 2. This will 2. Of course, we have here second to the power negative 1. This 2 will be cancelled with this one. So what is the leftover? The leftover is mole to the power negative 1 dm to the power 3 multiplied by second to the power negative 1. So it's easy to derive the unit for the rate constant, and it is a common question in the exams. How many orders should we study? We have only 3 orders. Zero order, first order, second order. What about this third order? This is an overall order for the reaction. But with respect to the reactants, we have zero order, first order, and second order with respect to one of the reactants. Okay, the last very important point in our interesting lesson is application time. We have to deduce the rate expression from experimental data. We have agreed that we cannot use the chemical equation to deduce the rate expression. We should have an experiment. We should have data from experiments. Let's check here. We have here, this table is giving us indication. So we have here different experiments. We have experiment 1, 2, 3, 4, and they have changed the concentration of the reactants. Reactants A, B, C are making this product ABC. And we would like to know how changing the concentration will affect the rate. We have here some guiding steps. What are those guiding steps? Compare between the change in concentration and the change in rate. Deduce the order with respect to each of the reactants. Number 3, the order should be the power of the factor of concentration change. This is very, very simple step here, or very simple problem. What we can do is we have to check how changing the concentration of each of the reactants will affect the rate. Do you hear that? Changing the concentration of each of the reactants, not all the reactants. We cannot check all the reactants at once. No, we have to study each reactant. For that reason, you have to, for example, I'm going to study A now. How changing A will affect the rate. But we have to check two experiments, because you are comparing. So you have to compare between first experiment, second experiment, or second experiment and third experiment, or first experiment and third experiment. So we have to only choose two experiments. But any two experiments? No, not any two experiments. We have to choose two experiments where A is changing, but B and C are fixed. Why? To know how changing A will affect the rate. But if you choose two experiments where everything is changing, it's not going to tell you how changing one of the reactants will affect the rate. It's like a mix between everything. So let's check here. Let's apply. Let's check experiment 1 and 2. What has happened in experiment 1 and 2? A has changed. Good. We can study here the effect of changing the concentration of A and its effect on the rate. But we have to make sure B has changed? No. C has changed? No. Very good. So we can use experiments 1 and 2 to check the effect of A on the rate. Effect of A on the rate. A has been increased by a factor of 2. By a factor of 2. A has been increased by a factor of 2. What has happened to the rate? Nothing. So we should understand directly that this is zero order. This is zero order. What does it mean by zero order? Changing the concentration is not affecting the rate. Changing the concentration of this reactant will not affect the rate. Very good. Let's check B. Which experiments should we choose here? Which experiments should we choose here? First of all, let's check experiment 2 and 3. Experiments 2 and 3, okay? 2 and 3. Why 2 and 3? Because B has changed, but A has changed as well. So now we cannot use it. We can't use it. So which experiment should we choose? Where B is only the reactant that is changing and the other reactants are the same? Let's check. Okay, 1 and 3. Oh, yes, 1 and 3. Why 1 and 3? Because A is fixed, C fixed. From 1 to 3, A same, C same, but only B. What has happened when we increased B? When we increased B by a factor of 2, what has happened to the rate? It has been increased by a factor of 2. Very good. So we should understand that this is first order here, first order with respect to B, because the rate has been increased by the same factor of changing of the same change to the concentration of B. The rate has been changed as the same change that has happened to B, so it is first order. Okay, very good. I think now you have built an idea about our steps or how we are constructing our answer. Let's check for C. Can we choose experiments 1 and 2? No. C did not change. 2 and 3? No. 3 and 4? Yes. Why 3 and 4? Yes. Because C has changed, B same, A same. Very good. So I'll use 3 and 4. What has happened to the concentration? By a factor of 2. What has happened to the rate? By a factor of 2. So it is first order. This is a first order. So R is equal to, let's write it. So R rate is equal to K rate constant multiplied by the concentration of A to the power 0. Should we write it? We can erase it because it is to the power So we can write it as the following: B and C. Okay, this is for today. Hope you understood this interesting lesson. Very important to apply, very important to repeat this video if you are wondering about the rate equation, how I can write rate equation, how I can write rate expression, and how I can check the order of the reaction. It is, yeah, it requires some brain work, but it is really interesting. See you later.